Hello everyone, my name is Mr. Rogers, and today I will be your instructor for learning technical art for the first time. In this video, we're going to be talking about how to do those cool effects you see with code using shaders, like this spiral, for example. I don't cover this exact spiral in this video, but I do cover a lot of foundations, so you can end up learning on your own rather than just being stuck. So I talk a lot about like AI and how you can use that to help you learn, and also a little bit about validating AI and things like that. So you should be familiar with the basics of Blender nodes and the basics of Three.js. You don't have to use Blender nodes if you're a node artist in another software. The knowledge will also transfer, but I'll just be transferring Blender node logic to TSL node logic. I'll cover that in a little bit. So unlike my other videos, there's no actual final project here. It's just a bunch of foundational concepts. So you can follow along writing the code if you want to, but you can also just watch and then pause the video when you don't understand something, write it down, and so on and so forth, and continue the video that way. So there are a lot of optional chapters that you can see in the YouTube description. So feel free to skip those if you want to. I do recommend watching them, but it's up to you. And of course, like always, source files on GitHub. Without further ado, let's get straight into the video. So what exactly is a technical artist? Well, kind of like what I said in my intro course to creative web development, if you saw that, it's very, very broad, and sometimes like the job title will be like creative technologist, but you essentially do what a technical artist does and like vice versa. So there's really no set definition. But the reason we distinguish it is probably because of like specialization, also like payrolls and economic reasons as well. But it's also kind of like more intuitive on what someone sort of prefers along the artist chain, if that makes sense. So typically a technical artist is a lot more math heavy than a traditional artist. So I don't know if you've seen this, but like these Blender competitions where people submit like really, really cool and high fidelity videos, animations they made with Blender or other 3D software. And you can think of this as a much more traditional art role in the sense that they're not really, other than optimizing for their own computer and render times, they're not really optimizing for other technical constraints beyond their own operating system and beyond their own 3D software. They're just focused on making something very, very visually stunning. Now, a technical artist, specifically since we're working with the web, I should do technical web artist. So what a technical web artist will do, will kind of look at traditional art and honestly even create traditional art themselves, but see how that can work within the web limitations and web restrictions. There's a reason softwares like Houdini and Blender and other 3D software, you have to download those as separate applications rather than them just being in the browser specifically. Because the browser itself has a lot of technical limitations, and there are tools like Blender on the web, like Spline, for example. But when you compare Blender to Spline, you can see that Spline is a lot more limited than Blender in terms of capabilities. And that's just because of web constraints. So maybe like a certain post-processing effect in Blender would render perfectly fine, whereas on the web, it would probably crash iOS devices. So a technical artist will think about how can we get a similar effect, but have it not crash iOS devices and things like that. So it's a lot more constraining than what a typical artist would be constrained to. And a lot of technical artists do traditional art as well and vice versa, so you don't really have to constrain yourself. There's a lot of absolutely goated people out there that do everything from art, technical art, creative technologists, call them whatever you want to call them. Here is someone, I don't know how to pronounce his name, I think it's like Renaud or something. He does 3D modeling, he does technical art, he does open source contributions, he does algorithm studies, he kind of does everything, and that's why he's a CTO, chief technology officer. And then here's another living legend himself. Again, he's kind of does everything. He does 3D modeling, technical art, whatever, blah, blah, blah. So it's really hard to categorize him. He pretty much does everything. He has worked on projects like Igloo, if you've been in the space. If not, definitely check these out. These are like next level websites with absolutely mind-blowing skills. Just crazy, especially all the optimization to get this level of fidelity in the browser. And they recently just worked on this one as well. You can also visit at the URLs here. You can see it's got the toon shading and everything like that, and having this in the browser is what makes it next level. Yes, if you download this as a standalone game, it might not be as impressive, but the fact that it's in the browser makes it significantly more impressive. And there's really, really so many talented people out there. I can't really shout all of them out, but here is another. He's one of the pioneers, so he's like top of the top. he is the top pretty much. um, but yeah, he's made like this is basically like a Pixar animation in the browser, but he did it with code. Like everything you're seeing here is code. It's not like with shader nodes or like rigging or anything. It's like actual mathematical code. Because at the end of the day, computers communicate in zeros and ones. So you could just technically code it all out yourself rather than use a 3D software. And that's exactly what he did. And this is the same thing. No 3D modeling software used. He just did the hard coded code himself. So yeah, definitely don't compare yourself to these people. They're just like at the top of the top. I'm not even close to them either myself. So, but it is just really inspirational to see what you can do within a browser once you understand the technical constraints, and then also how to contribute that as the technical art field kind of grows within the browser. So that kind of segues directly into my next point or topic: why become a technical artist for the web? Well, browser capabilities are growing, and a little bit more on that later, but they're growing, so this field is also growing. And the second point, probably the biggest point, is like it's fun and very stimulating because it uses like all aspects of your brain. You can be creative, but you can also be like logical at times and things like that. So you kind of like the full range and you kind of like never get bored, which is a really, really cool part about it. And then the third thing, it's cool and it's like a new medium. When you think of like 3D art or like 3D work, it's typically either just like photos, like rendered photos, or like rendered out videos and animations and movies, or you think of like 3D printing or like physical mini dioramas and things like that when you think of 3D work. But sometimes you don't want to buy all these physical things and place them around your house. They might collect dust, it might be, a little bit annoying and whatnot. And then sometimes when it comes to like videos and rendered animations and things like that, you want to like actually interact with the characters. And then you also have like downloadable games like those on Steam, right? But you never really have like these really, really cool high fidelity ones in the browser. So there's like some sort of new medium in a sense. It's not really a new medium because we have like browser games and a lot of browser games have gone like really big too as well. So it's not really about that, but it's like a growing medium in like introducing game dev and also merging like web dev. It's about like creating worlds and experiences rather than just like separating, oh, this is a website, this is a website, this is a game, this is a game. It's kind of like merging those two branches. So it's like a quote unquote new medium. And what makes it so cool is that it's accessible because all you need is an internet connection and a device and you can access it. And that's like really, really cool about it. And if you're like more into business, making money, that sort of stuff, or like being competitive and whatnot, yes, there's a huge competitive advantage aspect of it as well. Like products and services today are so similar. It's like less about what your product and service actually is, because that's just about like maintaining the status quo. And now it's more about how do you make people feel rather than like what your product or service actually gives them. And one way to make people feel things is having cool websites and like accessible technical art. You don't have to like buy physical products. They don't have to download games or spend money or whatever. Like, right, it's all in the browser. So yes, there's definitely a huge portion of this as well, but that's not really the focus of my video. This can definitely be one aspect of your motivation, but don't let it be your primary motivation. Let these be your primary motivation, and this will naturally come as a byproduct of your other intrinsic motivators. So the last topic I just want to talk about is like why not be a technical artist for the web. Well, the first point is it's very, very competitive and very niche still. Even though the field is still growing, it's still very niche, and because it's very niche, it's very, very competitive, and you're competing with people that work 10, 12, 11 hours a day just because they really, really find it interesting and fun. So if you're one of those people, by all means, you can totally get into it. Of course, there's like technical artist roles where it's not that competitive or not as competitive as the web, but being a technical artist for the web is really, really niche and very, very technically demanding. But maybe you thrive on a challenge, and then in which case, yeah, by all means, that doesn't really matter at all. And then the second thing I want to talk about is like still stagnation and atrophy. Once you get into like a design agency, they might like you pigeonhole you into a specific task or a specific skill. And then you might want to do like more artsy stuff, but then you won't have the ability to do artsy stuff on the job, which is fine. I mean, you can do that like outside of work and whatnot, but then you're like spending a huge chunk of your life not developing skills in those other domains, even though you want to. So that's also like a trade-off. If you try and put yourself in the frame of being someone that does art and like technical stuff, but then you're only doing technical stuff at the end, it really like gnaws at your self-confidence and makes you feel like you're stagnating if you don't find the right job. Of course, not everyone is like that. Some people are totally fine, like, ah, whatever. That's what I wanted, but I'm just gonna be happy with what I have. But then there are other people where if you aren't using those skills, it feels like you're stagnating. It literally feels like you're wasting your time, even though you're being paid for it. It still feels like a waste of time and it like drains your mental health. So definitely consider which kind of person you are there and how much weight you actually want to give to this role, because it will kind of like take at you if you're not passionate or if you want to develop your skills in these areas. So either find the right environment or know that there is the possibility that you get pigeonholed into doing something you don't want to do and aren't able to grow your skills in other domains. Okay, so now let's take a look at TSL, or in other words, Three.js Shading Language, and what it is and why it exists. So I highly recommend visiting this URL over here just to read a little bit about it. Come back to this, but before we talk about TSL, I just want to say that it's part of a larger movement of the web as of the current moment, transitioning from the WebGL standard to the WebGPU standard. So if you have no idea what I'm talking about, you can take a look at the WebGPU API documentation. It kind of talks about WebGL and WebGPU. Now this might be a little bit more technical than intended, so I'm just going to give like a high level sort of conceptual understanding of what's happening. So you don't really have to be technical to understand it. It might not be 100% accurate, but intuitively it's very conceptually similar. So basically, we have computers, and computer language is zeros and ones. And in the very, very old days, we used to have like those huge, large machines and we would like pick and plug stuff in. Like we're pretty much coding in zeros and ones, but no one really likes programming that way anymore, right? So we create like a low level programming language like C or C++. And then C and C++, it's very low level language, which means it's very close to computer code. It's like harder to understand for humans. So we create a even higher level language like Python, for example. And Python, I think, is actually based in C. And then because there are people that don't want to touch code, well, we use code to build things like applications. Blender is primarily written, I think, in C++ and C as well, but there's a lot of Python use cases in Blender as itself, which ultimately, at the end of the day, does compile to this and write over here. So it's not a complete, accurate sort of representation, but the whole idea is like we go from lower level and we abstract it to a higher level language, and then we abstract it again to use like a user interface, for example. That does not mean Blender is easy to learn. That does not mean Python is easy to learn, or it's just like we like to abstract things to increase usability and accessibility. So that's the same exact thing when it comes to Three.js, or any sort of coding library for that matter. The web standard for rendering 3D graphics in the browser used to be WebGL, but WebGL, due to like technical reasons, isn't as powerful as the new standard which is coming in called WebGPU. Three.js was a library that they took this low level sort of code like WebGL, which you can think of like is kind of like C, and they did a bunch of JavaScript and WebGL code. So we could just use something like a camera, right? We didn't have to write the math for a camera. We could just do like 3.camera. Because the Three.js library maintainers, they wrote all that math, so we could just use a camera rather than creating our own camera with low-level code. So now what they're doing is they're upgrading the library to use this new web standard, WebGPU, which is going to be faster and have more features than WebGL. But since WebGPU is still in development and WebGL is probably not going to go away for another few years or so, which is why they created TSL, which is a new way of writing shaders, and it will automatically by default detect your browser capabilities and compile down to either WebGL or WebGPU. However, that's not the main reason they created TSL. If you go back to the documentation of why they created TSL, it's because creating custom shaders like using low-level languages is very, very confusing and hard to pick up and time-consuming. Like the way Three.js is now, you either have to use like their built-in shaders that they created for you, or if you want something complex and complicated, you have to dive deep into the code in Three.js and modify their code and get into the low-level language weeds, or completely start from scratch and create your own like Three.js library pretty much, or create a custom shader with Three.js or whatever. Either way, you have to go into those lower level languages, which is very time consuming to understand and learn. So you kind of only have those two options. So they pretty much created this third option called TSL, which uses a node based system, except it's kind of like represented by text rather than like visual nodes because it's still coding at the end of the day. So it's like a medium between using an actual 3D software node system and writing pure low-level language shader code. So if I come to the source of Three.js source nodes nodes.js, you can see some of all the active nodes at the moment. So some of them you might recognize from your other node softwares that you've been using. For example, there's like a blend mode node, and you can see like burn, dodge, overlay screen, so on and so forth. So if I go back in Blender and search for a mixed color node, right over here, you can see if I go to like blend mode, you can see like stuff over here. Again, it's not one-to-one, but I'm kind of just showing you some similarities here. So you can think of that node like a mixed node. Of course, not one-to-one, but that's the idea. And then there's like a bloom node here, which I'm assuming is for like post-processing. And if I go to a glare node, it's kind of like the glare node in Blender. I know it's also like a check marks and like EV and whatnot, but here you can see bloom. So you can think of bloom node like the glare type of bloom for the Blender node. Of course, Blender has a lot more features for its glare node, whatever. But the entire idea is to like have these nodes written in code to make programming a lot more accessible for artists. And here you can exactly read that. The aim of this project is to create easy to use environment for shader creation, you know, even if they have to suffer and create the complexity behind it. So shout out to all of them. And if you got some money, definitely consider donating to the Three.js maintainers out there. Now you might be asking, Andrew, why don't they just create a node-based system like Blender or Unity or cables.gl in the browser, make that instead of TSL? Well, again, you know, they only have so much time, and creating a node-based system would kind of like bloat the library, make it larger to download, and they would have to implement that too. So it's like, so TSL is kind of like a blend and a compromise, and also kind of like an optimization all at the same time. Okay, so before we dive into actually learning TSL syntax properly and everything, I kind of just want to do some intuition-based learning first, and I'm going to be doing that with Blender shader nodes. If you're not familiar with Blender shader nodes, but like something else, maybe like cables.gl or like Unity shader nodes or Unreal Engine shader nodes or something like that, you will be able to apply those concepts over as well to TSL. But for this video, I'm just going to be using Blender. So you can get the starter files on my GitHub. It might be a little bit in a different location and it might look a little bit different from what I'm showing you now, but it's a very standard basic Vite application with a basic Three.js setup here. The only main difference is that I'm having some TSL imports, so we don't have to import them ourselves and copy and paste all the time or like do the enter check thing. Sorry, let me close this. And instead of importing all as 3 from 3, we're importing from 3-WebGPU. And that also means we are no longer just using the WebGL renderer, we're using the WebGPU renderer. In the future, this is probably just going to be import all as 3 from 3, but at the current moment, we're going to have to do 3/WebGPU. Everything else in this document is a standard Three.js scene, except I am loading a model and creating a plane. And both the model and the plane use the same custom material that we're creating over here. I called it create basic grayscale gradient material because that's what we'll be starting off with. And instead of mesh basic material like you use in traditional Three.js, we call it node. So mesh basic node material. Then there's like mesh standard node material, etc., etc. And don't worry if you don't understand what's in here at the moment, I'll get to that in a little bit. So we can just run npm run dev to open to our local host and just take a look at what we have. So this is what we have. I added an axes helper just so we could visualize the axes, but here's my loaded model and here is my plane, both using the same exact material. Okay, so before we cover TSL and like the syntax and how it works and everything, I kind of want to do some intuition building first. So if you're not familiar with what you're looking at here and what is being output on the surface and you have like no idea what you're looking at, I highly recommend getting a little bit more familiar with Blender nodes. I do have a video on it over here. You can start from about 407 and end about 455 and you should be able to understand what you're looking at here. But if you don't, you know, obviously there's a lot of other teachers out there in Blender tutorials on nodes, so just find someone that you vibe with and get a little bit more familiar before continuing on with this video. Okay, so I added a small plane here. I'm just gonna hit Shift-Alt-Z to get rid of the overlays real quick. You can also come here and turn that off. Or if you have the more pie menu options on that I showed in previous videos, you can just toggle that on and off as well with the Z key, really up to you there. But just as a quick refresher, what we're looking at here, we're using the gradient texture. And by default, the gradient needs to know what direction it goes in. And by default, it's just in the positive X direction. So here's just a screenshot. We're looking from this over there, so it's going to be going to the right. And this is exactly why we see over here. Now, it's not perfectly centered over here because of the color ramp. So let's just do that. So now it's back to the center over here. Now the texture coordinate system that we're using is the object. So basically just the object's coordinates in its local space. So if I move this or rotate it, you can see that it still looks the same no matter how I rotate it or move it. Okay, so intuitively, what does that actually mean? Because we're going to be working with object for this tutorial when we work with TSL. So I just want to talk about that a little bit more intuitively and what that actually means. So what that functionally means is, I think by default in Blender, let me just turn that on. By default, if you add a plane to the scene, it will be 2 by 2. And the reason we choose 2 by 2 is just because it's a lot easier to work with intuitively for artists and people that aren't really math, because you're normalizing like -1 to 1. And Three.js, the starting by default, if you set nothing and add a plane, it's actually 1 by 1 plane. So your coordinates is going from -5 to 5. So just to drive that point home, you have a 2 by 2 plane here. So you have a 2 by 2 plane. So if your plane has a height of 2 and a width of 2, we need some sort of coordinates to represent that at your vertices. So at this vertice, it's going to be 1, 1. At this vertice over here, it's going to be -1, -1. It's going to be 1, -1. And then over here, it's going to be -1 and 1. Cool. So if we do the math, 1 minus 1 is just 2. So here you can see a width of 2, and you can just do the calculation for all the other sides as well. So this is the coordinate system that we are using for our gradient texture over here. So let me actually just get rid of the color ramp real quick because it's changing the colors up, and let's just look at the gradient texture itself and take a look at why are we getting black and white values kind of looking like this. So probably more of a refresher if you watch my other video, but remember, we represent colors on like computers and stuff like that with RGB, and a very common method is to do that between like zeros and ones. And 1 means most of that color, and 0 means the absence of that color. So 1, 0, 0 means all red, and this would be a completely red color. And then we can like mix colors. So if we do like 1, 1, 0, for example, let's just change this over here to 1, 1. We get yellow, and if I go here, you've probably seen this before, like max greens and reds mixed together make yellow, and everything in between, sort of like that. So because the directional vector for the gradient texture by default is in the direction of, sorry, it should be 1, 0, 0. This is the direction that the vector is pointing in, positive in the x-axis, not to be confused with the color representation. It's also vector 3. It's going to get a little bit confusing here. But this is the direction that the directional vector is looking in. And again, more refresher concepts here, but all points in 3D space technically are vectors, but we've distinguished between vectors and points because points generally don't have a magnitude or like a direction associated with it. So vertices, for example, are like points, but they are technically also just vectors. So we want to start at 0, 0, 0 of our plane object. So where is that, given our coordinate system we addressed earlier? Where would that be? Well, that would be right here. So this would be 0, 0, 0, just like this. In the previous video, we used the generated coordinate system. So 0, 0, 0 actually started down over here. But for this video, it's actually going to start right in the center of the plane because this time we're using object rather than generated. And if you remember, we take the dot product of our two vectors in space to determine what color we see at what exact point. So let's just throw a dot and say I want to find the color at this point. So we can draw a directional vector from our 0, 0, 0. So let's just say that's about -0.7 in the x direction. And in the y, let's also probably just call it 0.7. So the full vector of this point over here, it would be, let's see, it would be -0.7, comma, -0.7, comma 0 because it's just a plane, so there's no actual z. And then we want to take the dot product. So we take its x and y and z channels, multiply them together, and add them together. So let's just multiply by our default directional vector. For the gradient, we're just going to get negative 0.7 plus 0 plus 0. So what's our final result? Well, our final result is negative 0.7. But remember, we are clamped between RGB and ranges between 0 and 1. Negative 0.7 doesn't exist in that range. So what it does is it just clamps to 0. So if you take a look over here, that's exactly why we see black. And that's exactly actually why we see over here, everything over here is black. Because at the center over here is 0, 0, 0, which means the farthest point over here is negative 1, 0, 0. So that means any range between here, between 0, the center over here, and over here is going to be a negative value. And because you can't have a negative value below 0 to represent a color, it just returns 0. So that's why all of this is just black. Y and z is irrelevant here because we're always going to be multiplying by 0 in our calculation. So the only coordinate that actually matters is this one. Now it does return 0, but didn't you say, Andrew, that colors are represented with 3 of these, R, G, and B, right? And isn't black 0, 0, 0? So if it just returns 0, then how are we getting black, right? Shouldn't it be 0, 0, 0? So yes, technically it actually does return a value, a color value of 0, 0, to the computer, even though our mathematical calculation just gave us 0. It's just going to uniformly assume that all your channels are going to be 0. You can prove that with more complicated node setup, but we're going to be talking about this a little bit more in the code. Right now it's just about intuition building. But yeah, you'd be correct, and a little bit more on that later. Okay, cool. So if you want to do that over here, like 0.1, and remember 1, 1, 1 is how we present white in RGB. So it's just going to uniformly, as we get closer, this is just going to be getting closer and closer to, so 0.9, 0.9, 0.9, right? And then you can just do it for any value over here, and it's going to get closer to that uniform 1 value. And that's why we see this slight gradient over here from black all the way to white. So we have this mapping node here that we can use to affect our texture coordinates or our object coordinates. And by default, Blender will do that dot product with our gradient texture, which again is always in the positive x direction, 1, 0, 0 by default. So we're just going to take the dot product of whatever we created over here to this directional vector over here. If you hover over the location here, you can see it's the amount of translation along each axis. So you can pretty much think of that as like adding or subtracting away from your coordinate system. And remember, no matter what our object y and z coordinates are, it's not going to affect the end result because this is always going to be multiplied by 0 and 0 in the y and z components. So here you can see I can adjust y, adjust z, nothing is changing. However, when I adjust x, you can see something is now changing because that's the only value that's being multiplied by 1, or a value where we actually get anything back. So let me just reset that to 0. And if I wanted this side to start at 0, how much would I add to the x location? Well, I would add 1 because on over here, it would be negative 1. So if I wanted to start at 0, I would just add 1. So I just add 1 there. And now you can see we start at 0 and then we head up to white. Now, what we're actually seeing is we're going to 2, not 1, because over here is 1, and we're adding 1 to that. So we're actually going from 0 to 2. And since we're clamping from 0 to 1, that 2 value is just irrelevant for us. Anything above the center over here is just 1, 1, 1. It's all the same color over here. So this is the only place that's being like a gradient, and then everything after that is just a flat solid color. So just to be clear, it's over here. We're adding 1 to it. This becomes 0, 0, 0 now. And then over here, this becomes 2, 0, 0 after adding 1 from the mapping node. We can take the dot product. This is just 2 times 1, 0 times 0 times 0. And then we just clamp to 1. So same thing. And then it just returns 1, 1, 1 as this color. So if I keep adding to this, you can see that it's not really going to do anything at a certain point, because now adding 152, it's just going to be 151 to 153, and these are just overkill above 1, and they're just going to clamp back down to 1. Now you might be saying, Andrew, what the F are you talking about? This doesn't look white at all. And that is just a color management issue. If you come over here and into render properties, go to color management, and then change this from AGX to standard. Now you're going to see that it's more white color here. I'm going to be leaving that standard on for the time being because that's what we're going to be seeing more closely visually when we start working with Three.js and TSL. Okay, so if we go back to the code, again, you don't really have to know about the syntax or whatever. And I'm using Y here. Let's change that to X. I also changed the variable name from P to final color. What we're doing here is using positionLocal and its X property of positionLocal. So if you look at the Three.js Shading Language documentation, or sorry, not official documentation yet, but wiki sort of thing, you can see that positionLocal is its local position. So it's essentially the same thing as our object texture coordinate system over here. Now you can see there's some other ones here, just the same as Blender. Not all of these map one-to-one to Blender, but there are a lot of things that will get you somewhere somewhat close, just with some slight modifications. So like position world, it's like where the vertices relative to the world space that you're in, right? So we were just talking about local coordinates relative to the object wherever it goes, but these vertices, they also have like an X from the world origin, right? The 0, 0 here, we're drawing a directional vector to know where to place it in the world space, right? So if we wanted to do this one, well, it's along the x-axis, so it looks like 2. So it's probably -2 and then 1 in the z-axis. In Blender, z is up and down, and Three.js y is up and down. Anyway, the point is this vertex also has a world space coordinate, but we're just working with object coordinates, so local coordinates in a sense. So you can think of the object here, texture coordinate, as the position local node that TSL provides that you can just access over here. So if I refresh the page on the code over here, you can see what we're seeing over here is very, very similar to what we see in Blender over here. How cool is that? Now this rock over here, it's not going from left to right because I rotated it along the y-axis. So here you can see when I apply my rotation, you can see now it's going from left to right, 0 to 1. By default, if I do Alt-R to reset its rotation, you can see this is what it looked like originally, and then I just rotated it like this. And I never applied rotation, so that's why it's also like here. You can imagine that this also has this rotation as well applied to it, not applying rotation where everything becomes 0 again. You can also apply rotation in Three.js using like a matrix, and it will reformat it the same way that if you do apply rotation, it'll reformat it to look this way as well. But for the time being, we're not going to be concerned about that. I just want to show you that it looks very, very similar. Now you might be looking at this and you're like, wait a minute, why is this thing on the right here look so close to this? Whereas this on the left, it does kind of look like that, but it's a lot more dull and muted. Is that because of the color management again, or is it something different? Well, it's actually something different because I'm using a mesh basic material for my shader material, mesh basic node material, which means it's not affected by lighting, so it should be fairly similar to what we see in Blender. The reason it's not is because when I created this plane, it's a 1x1 plane. In Blender, it is a 2x2 plane. So what that means is over here is -0.5. Again, it's just all the way going to be here until the 0, so this is all black. But this goes from 0, not to 1, but to 0.5. So you're not actually seeing white here, you're just seeing gray. So if you want to fix that, all you have to do is come over here and change this to 2x2. And if I go back and take a look at my plane now, sorry, it's kind of like next to the axes, but you can see that it's actually going to white now. So let me undo that. So let's just do that in Blender. If I left click and drag down to select more than one field and just enter 1, you can see now it's scaling 1. We still don't see the change yet because we need to apply our scale. So if I apply a scale, now you can see this is exactly what we're seeing in Three.js originally. And if I scale this up, you can see it's not really going to change anything because of the scale, but as soon as I apply my scale, it's going to fix itself. And that's the exact same thing that happens in plane. Here, it's going to be that dull color again, or that gray, right? So if I just do plane.scale.set, I think it's auto-correcting, and let's just do 5, whatever value. And sorry, where is scale? I think I have like prettier format or something that's messing up with it or whatnot. You can see I just get a bigger plane, but I don't see the white. I still see that gray. So that's the difference between updating like the coordinates and the scale and all of that sort of stuff. Again, a little bit more into the weeds, but hopefully it kind of clears up things a little bit. Okay, so let's get rid of that. And now we're back to this. And that's actually exactly the same reason why you don't see white on top of this over here, because if you look at it, it's not actually going to the value of 1. So if I do like SZ and then apply the scale, you can see now it's going to be white over there. Now, there was some modifiers that was messing it up after I applied the scale, but that's beyond the point. If I go into edit mode and just do it, you can see that at a certain point it's just going to be all white, because all I'm doing right now, it's like after the points go past 1 in the z-axis, it's just going to return the white value over there. So if you watched Blender tutorials before, you know if you scale in edit mode, it's not going to affect your scale value. Is actually going to affect your object values itself. So here you can see that it doesn't change the scale in there. But yeah, so that's another way just to check that. So if you wanted to measure this, I'm sure there's like a measuring tool or something. It's not going to be 2x2 thickness. Yeah, it's only one thickness. So this is also going by 2, like 0.5 and then negative 0.5 essentially. And that's why it looks so similar to the colors over here. Of course, we always want to close it up with the documentation here. So if I look up the gradient texture node, you can see we did set it to linear and it directly outputs the x coordinate only. So we did only basically talk about the x coordinate, and we know the range values there, and that's exactly what it's doing. It's just outputting those directly, and that's why we got such predictable colors that we did. Now you might be wondering, why does it say just directly outputs the input x coordinate? Why doesn't it say to do the dot product and everything in the documentation? Well, this is like a really big thing with when it comes to documentation. It's less about being technically and very specifically accurate and more just about ease of use. Especially since Blender, the whole reason Blender exists is to specifically try and abstract all that mathematical knowledge behind the scenes so you can just focus on creating stuff with intuition rather than having to dive deep into the math about it. Then functionally, this is exactly what it does. The x and y coordinates don't matter at all, just the x one. So instead of explaining all that in detail, you can just simply tell a user that it directly outputs the input x coordinate. Now you might be wondering, okay, why did they choose positive x? Why not positive y or positive z? Well, no one actually knows that answer for sure. It might be because of the coordinate system they use, or the fact that when you do something, it's usually x comma y comma z, right? So if x is the first coordinate, why not just use that as the default directional vector for the gradient texture? So we can actually just use the gradient texture itself because it does have its own, technically, its x system from 0 to 1, right? So I'm just gonna completely delete this, or actually I unhooked it, so it's the same thing. And I'm just gonna plug this in here. It actually doesn't really matter if it's the color factor, so you can use either one, and I'm just going to delete that one as well. And take a look at our plane. We're now going from 0 to 1. So it's very similar to the generated coordinate system here. So it's just going from 0 to 1 in the x. This one is doing that as well, but again, remember this one is rotated, so let's do Alt-R to reset its rotation. Now, it's supposed to go from 0 to 1, because we're no longer using our object coordinates anymore. We're just using basically generated coordinates from 0 to 1 across your object. So why don't we see anything? Well, it's actually because we have all these modifiers on here. If I do F3 and convert to mesh, you can see as soon as I convert to mesh, now it's going from 0 to 1. So, or you could just get rid of them as well. And you can see that for this left point is black, and over here, the versus right point is 1. So obviously it's not even right now. Like this is more to the x, which is why that's lighter. But I can just like move that over there, and now you can see over there is a black point. And then if I just really want to do that, I can do like x0, just flatten it out, and now that whole side is black. And if I move it up and down, it doesn't really change anything because again, the z and y axis doesn't really matter whatsoever there. Super cool. Something really fun you can do is go into edit mode, just select these and just start moving it. So let me turn that off, and I'm just going to start moving. You can see as I go into the negative x, all of those are staying black. But as soon as I start coming over here, this side is turning black. You can see right there. And then now it's over there. The center is now black. And then over here, the center is now white, and so on and so forth. So you kind of get the point there. You can do that for this one as well. And now if I move this one, it's kind of almost like a window sort of clipping, cutting out wherever you want to go. So hopefully that makes sense. So I'm just going to select the whole thing in edit mode. You can't see it because I have overlays, but you can see it's pretty much acting like a window. Now, if you don't understand what you're looking at right now and how it works, or it doesn't really make intuitive sense to you, I highly recommend either revisiting some portions of the video and trace out some numbers. Like, just honestly, that's exactly what I did when I didn't understand something. I would just like pick a point and then just see why I see the color that I see at that color. We have all the foundational knowledge of, how to get all the necessary information to calculate things, but sometimes you just have to like sit down and calculate it in order for your brain to pick it up. I mean, there's so many times where I thought I intuitively understood it, but I just had to like sit down for like an hour and, really write down everything step by step until I got it. So it's really nothing to feel embarrassed or ashamed about. So if I apply my location, what do you think will happen? Before I give you an answer, I just want you to really, really think about it. And when I apply location, you can see the origin point is going to reset back to the world origin. So if I move here and move it over here, I should start seeing white just as I try and center my plane with the origin point itself. So if I do control period to go into the origin edit mode and I move that with G, you can see I'm actually technically moving the location of the plane in its local space, which is based off of this origin, while the world location of the plane actually remains in the same exact place. So I'm actually moving the plane by moving the origin in its local space, but the world space remains the same. And I'm just going to hit control period to resolve that. So the actual coordinate system now over here is the 0, 0, 0. So over here, it would be the width of 2. You can imagine that the plane is actually somewhere over here in its local space. So intuitively, then if I go into edit mode and just move it here, you can see we pretty much get the same thing. Or we can right click, set origin to geometry, and you can just imagine it like snaps back over there. And yeah, of course we have this mapping node here. So you can imagine it's like taking this and like translating the coordinates along there. And just to show you, gradient texture 0 to 1, if I use generated, it's going to be the same exact thing. Sorry, let me just reset this. And yeah, same exact thing, whether I use it or not. And in the docs, generated is a range from 0 to 1 bounding box. The last thing I want to briefly touch on before we touch TSL is that you need to be familiar with two kind of shaders. There's the vertex shader and the fragment shader. Now, if you dive deep down into the lower level language codes and all the processes, there's really a ton out there. And that's why it's so confusing to develop. But since we're working with TSL, all you need to know is that there's a vertex shader and there is a fragment shader. So the vertex shader is kind of exactly what it sounds like. It's like where your vertices are. So if you want to like move vertices like this, like let's say you have a triangle like this over here, and you want to move like this vertex over there, like in Blender you can just like grab it and move it, right? Well, in code it's like you can set its position or like add to its position or use like a mathematical function over time to move it maybe in like a circle over time, and this one also in a circle over time, and so on and so forth, to like rotate or whatever, or use linear algebra. So you can think the vertex shader as like affecting the vertices. And then you have the second one, which is fragment shading, which is the faces that your vertices make, like this triangle over here. It's like the color for that. There's a lot more details there that I'm skipping, like assigning data to vertices and things like that. I might touch that on future videos or even this one. But the whole idea is what happens first is the vertex shader happens first. They do stuff with your vertices, and then after they create fragments, you work with your fragment shader and color it in. I mean, that's how it works in Three.js, and that's how it works in Blender, right? You always create something first, like a plane or a mesh, and then you give it a material. So you can think of your material like the fragment shader, and you can think of your object that you created or added as your vertex shader. And just like it, you can update your, right now you can think of, I'm updating my vertex shader in code. This is what I'm doing right now. I'm updating my vertex shader, and then now I'm updating my fragment shader. Like, just like code, that's exactly how you can think of it. You can adjust your vertex shader whenever, and you can adjust your fragment shader whenever. Again, I do want to reiterate that this is very simplified. You can see there are other kinds of shaders in process here, like geometry shading or geometry shaders. If you look up geometry shaders, there's like stuff on that as well. And if you look at the TSL docs, you can see the fragment node for the fragment shader, the vertex node for the vertex shader, and then you have the geometry node here. I think this is more similar to geometry shaders, like part of the GPU pipeline, compared to the geometry nodes in Blender, which I think runs on the CPU. So don't confuse the two. I'm actually not sure. I would have to look into this a little bit more. Primarily for this video, we're going to be working with the fragment shader and not so much with the vertex shading at the moment. Before continuing on, you don't have to do this, but I highly recommend at least watching this video from at least this chapter here. It covers a lot of intuitive concepts. It does go through a lot more detail, which I highly recommend watching as well. Even if you don't pick up the technical details, there will be some intuition development that'll help you in the long run. But here you can see, like, this is what I briefly kind of like went into the weeds and touched on a little bit more there. But you have like model space coordinates, like local space pretty much, right? The object itself, the coordinates of the object, world space where it is in the simulated 3D space. You can see they used plus grids to represent that. Then there's like camera space, where is that object relative to the camera? And then how do we transfer what the camera sees to your view screen, or like your computer screen pretty much, which is like, you know, your 2D sort of things. So it's just a bunch of math over and over and over again, and it's all taken care of for you behind the scenes. Okay, so let's revisit the starter files, and I want to reorganize it so it's a little bit easier to understand. There is nothing wrong with this approach by any means, but I just want to reformat it so it's a little bit more clear what we're doing. Like, just for context, if you look here, you can see I'm creating the node material and then I'm targeting the color node. So it's like, what is the color node? And then you come here and then you read that. And then you also come over here and see other things like emissive nodes. Is that emissive node like this? Or is it like the emissive property of a printable BSDF? And is the color node, is that like this? Or is that just like this where I search for RGB and then it's kind of like that? And the answer to that is, like, you can think of the color node like this, but you can also think of the color node like this as part of a larger node, but not necessarily a principled BSDF node, if that makes any sense. So again, it's not really a one-to-one translation. Just use whatever conceptual or intuition bridge you can to make sense of it, rather than trying to fit everything into a certain system, because implementation details are going to be slightly different. Okay, so I'm going to come back here and I'm just going to copy the three mesh basic. I'm starting with the mesh basic material just because I don't want it to be affected by lighting, but we're going to change it later so it is affected by lighting. I think, I'm not sure yet, I'm just recording. Anyway, now what we can just do is come over here, shared custom material, and we want to target the fragment node this time. And we want to set that equal to what we have over here. And then we can temporarily get rid of toVar. I'll talk about what that does in a little bit. I just want to make sure we see the same exact thing right now, so we should be able to get rid of that. Now we're not going to see anything with positionLocal.x because positionLocal is a vec3, and .x would just make it a single value, and fragment node is a vec4. So a vec4 is typically what we call RGBA, or red, green, blue, and alpha channel. Or you can think of it as X, Y, Z, and then W for the fourth coordinate. So we're not going to see anything at the moment, but if you get rid of X, you can see that it's going to show some colors. And even though positionLocal is a vec3, it does fill out the fragment node because it's smart enough to put the fourth value as just full visibility. So here you can see positionLocal is a vec3. And then if I go to the fragment node, you can see that it is a vec4. And then by default, the fourth channel here is going to be 1, so we can see it. If you want to try something out, you can totally do that. You can just type let me just come over here and do vec4. If you don't have the import, just search for it, just type it out and then hit enter and it'll import it for you. And if that feature is not working in your editor, you can just come up there and type it yourself, but it will automatically import it if you get the right one. If you accidentally forget it, just backspace it out once and then hit it again. I already have it imported, so it's not showing it up, but that's one way to do it. So we can make yellow, which is full red, full green, and then no blue, and then we can just have transparency to be 1. And now you can see, indeed, we do have that yellow color here. And again, it's smart enough that you don't actually have to fill out this. So if I do vec1, 1, you can see that it's going to remain fine as well. Or I can do vec3, same thing like here. You can see it's also going to work. There's a lot of other tricks that you can do. For example, if you want this, you can make this a vec2, for example, and like here, and it'll fill out the first two coordinates, x and y, with this vec2 of 1. And let's just make sure I have that imported. And you can see if I go back here, it's also working as well. And it's very similar. So if you wanted everything to be gray, you just do 0.5 and this will fill out everything with 0.5. And you can see that we have gray here. So if we wanted to see position.x, what would we do? Well, we could just put it right here. So positionLocal.x. And take a look. This is exactly what we have. So essentially, it's equivalent to just doing this 3 times. And here you can see it's the same result. I'm kind of getting a little bit carried away here, so let's actually get started now. And I want to first start just here with positionLocal because that was the object coordinates that we were working in with Blender. I'm also going to update the plane to be 2x2 so we see the same thing that we do in Blender. And let's also just go in Blender. Let's get rid of all the noise and just put the object coordinates directly into the material output. And oh my gosh, guys, look what we just did. That is totally crazy. And let's just move the plane a little bit more to the left so it's not over the axis helper. So in the past, we were doing the dot product between the gradient texture and the object coordinates. And now we're just using the object coordinates itself as the colors for every point. So here's like 1, 1, which means red and green are full 1. There's no Z component, it's a plane, so that's going to be 0. And then if you want to think of the alpha channel or whatever, you can think of that as well. So it's just 1, 1. In the center is 0, 0, 0. Anything lower on the left is negative, so it's just going to clamp to 0. Everything down here is going to be negative in the Y, so it's going to clamp to 0. So that makes sense. This whole entire thing is black. And you can do the whole same thing that we did last time, except you can just use the object coordinates rather than having to cross product it with the gradient texture. So if I want to, all I have to do is just go over here, E, and I'll just type 2, just to make it a 2x2 cube, and then Q origin to geometry, and take a look at what we get. Now we just added a Z component, or you can also think RGB. We added a blue component by making it 3D instead of just a 2D plane. Yes, technically 2D plane, 3D, whatever. And I'm just going to flip it so it's the other way, just so it's easier. But yeah, you can just do the math. Let's say we want to pick a point right over here. That's going to be negative 0.5, negative 0.5. So it's going to be 0, 0. But then over here, as we get over here, on the other side, what's that going to be? Well, the blue channel is increasing along this y-axis over here. So what does that mean? Well, on this same point over here, it is also negative 0.5, negative 0.5. But the blue channel now is completely 1 because we're on the entire other side of the cube. Whereas on the other sides, where we were originally, it was also negative 0.5, negative 0.5, but the blue channel was 0 because we're on this side. So you can imagine it goes from 0 to 1 in the blue channel on this axis. So if you really want to think about it, you can think up and down is how much green is in it. Left and right is how much red there is. And then the thickness or depth of it is how much blue there is. That's why it's also like X, Y, and Z. Yes, I know in Blender up is Z, but yeah, you get the point. So that's why when we do positionLocal.x, we're just like saying, hey, I don't care about the Y or Z channels, just focus on my object's X coordinate to determine the returned color for all the channels. This is not to be confused with the gradient texture we did the dot product with, even though the result is exactly the same. If you want to see an equivalent to that in Blender, you can search for the separate XYZ node, and it'll separate all those coordinates into the respective components. And here you can just see as I cycle through these what they're going to give back. But this is more accurately equivalent to what you see in Three.js. I know in Three.js it looks like we're setting the X coordinate for the Y and the Z. And in Blender it seems like we're not using Y or Z at all. Whereas in Three.js it seems like we're using all 3 of them because we're filling them out. But effectively, intuitively, it's kind of the same thing here. We only care about the X channel. You might come back here and just like, oh, well, that's how it looks in Blender, right? We just put zeros for Y and Z. Well, now we get a gradient of black to red rather than grayscale. And that makes intuitive sense because let's say you pick over here, we're now doing 0.1, 0, 0. And then over here is 1, 0, 0, so full red. In the past, if we had positioned local.x on all of them, then over here would be 1, 1, 1, which is white. Now we have 1, 0, 0, which is red. So just things to keep in mind there. Okay, so let's reformat our code so it's a little bit easier to work with. We could have done what we did initially with a regular JavaScript function, and you can see that it is possible just to use classic JS functions like I did initially. But there's this special function with TSL that allows you to access other special things within TSL that just makes your life a little bit easier. So I'm going to be using this. So let's just come over here. Let's just call it fragment, fragmentation equals fn. just a simple arrow function as per usual. And let's make a variable called final color equals, and we'll just slap this in right here. And then we can replace this with fragment shader function over here. And then we can just return final color and hope. And let's make sure to import fn. And cool, we get the same result. Okay, now go on GitHub and download the second set of starter files. It'll probably be just named starting fragment shader function. So the only difference in these new starter files is that I'm loading a new model here called scene.glb, but every item in the object is currently using the shared custom material. We're going to change that a little bit later, but for now, everything in the scene is going to use that same thing. So that's what you are seeing here. And then I just updated the camera position and target position, so it starts visibly like this. If you want, you can also look at the Blender file. It's a very basic, simple scene. And I'm just doing that because it's a little bit more fun than just looking at a plane. But all of these just use a simple gradient or just a simple color for their textures, and we're going to be texturing some of them later. So since we're here with the mapping node, we might as well just take a look at some common operations. If I scale, let's say by 0.5, you can see it's going to end up the same as our 1x1 plane here as well with scale of 1, 1, 1. You can imagine it is multiplying our object coordinates by a value of 0.5 in the x direction. So that means since this side was going to 1, 1, 1, now it's going to 0.5, 0.5, 0.5, which is why it's no longer white. And you can see that's exactly the same with our 1x1 coordinates, have coordinates going to 0.5, 0.5. So if you want to see the same thing in Three.js, well, you can do that as well. Just do multiply and then times 0.5. Now, if you look, our gradient is no longer going to 1, 1, 1. Now, you might be a little bit annoyed here because here we're doing positionLocal.x dot multiply by 0.5. But here we're doing basically positionLocal multiply by 5 and then .x. But when it comes to values like these, multiplication order doesn't really matter. So if I scale all the x, y, and z coordinates first, and then only decide to use the x channel after, I'm going to get the same exact result anyway. If it's easier for you to understand the other way, you can search for a math node. And by default, conveniently, the value is 0.5. Instead of add, we can change this to multiply. And now, of course, it's even more darker because I'm scaling this and then doing it again. So let me just hit M to mute both of these. And I'm just going to hit M to toggle this on and off. You can see the difference before and after. And then over here, before and after as well, it's the same exact difference. If you want, you can hold Alt key to quickly disconnect a node and keep it intact, but I'm going to keep it for now because I'm just going to work with one node instead of having to deal with all those other nodes. Okay, so I'm also going to undo that here as well. And for just going left and right, I'm sure you can figure this one out, but yes, there are functions like add. So if I do add 0.5, actually, let's choose a different value this time. You can see that it's going to shift it. Again, if you want to pause the video and do the calculation to see where the new coordinates are and how that works, you can totally do that. And yes, you can also have the add over here rather than after the vector. And if you change this to an add, you'll see that effect. And if you wanted to multiply and add, well, you could do that as well, or just use the mapping node to do both of those functions. Okay, so now I just want to talk a little bit about this rotation thing over here because it's a little bit more complicated. So if you think way back into math class, you've probably done something like this, where you had to rotate an object either around the origin or some other point of rotation, and you'd have to determine its new coordinates. Depending on a lot of things, you can find shortcuts to the way that you're doing things, but the general way we rotate something in 2 dimensions is using a 2D rotation matrix. That's represented like here, but also by these formulas over here, and then this is the inverse one. This one will rotate it counterclockwise, whereas the inverse will rotate it clockwise. But typically you just use this one and then you just flip the sign, like do -45 rather than use the inverse 45, just because that's easier, but honestly it's really up to you. Now, since this is an intro course, I'm not going to explain the math in detail here, maybe for more advanced courses where it's needed, but typically it's fine just to use it without really understanding the math behind it. If you did take trigonometry before or linear algebra, you probably have derived these before and understand where they come from, but for the time being, it doesn't really matter. Now, you might be asking, Andrew, how do I even know to use a 2D matrix? How do I know how to translate that? What if I don't know that, right? Like, I haven't taken math in a really long time. Well, that's exactly where AI comes in. And AI is a great self-learning tool, especially for artists that aren't familiar with math. For simple tasks like these, you can use it to provide you a direction, and then you can self-validate it later. So if you don't understand what it's doing here, Well, you can just ask it another prompt to explain what formula they're using. So here I said, can you explain what that's doing? Now they show me a formula and I'm still confused. Where did you get that from, man? And then it's telling me the 2D rotation matrix. So now I go into Google and I look it up and I see that it's consistent with AI. So that gives me confidence that my solution is going to be accurate. So since we're only using the X direction, we actually don't need the other coordinates there. So we can just copy this one. Remember, in Blender, we were rotating along the z-axis because that's up and down. So in Three.js, it's going to be a y-axis up and down. So we want this one over here. So I'm just going to copy and paste that into my code. And then I'm going to copy and paste this as well directly into my code. And then let's copy final color and just paste that over here and get rid of this with Control X. Cool. And now you can see it's rotated 45 degrees and you can just flip the sign if you wanted to rotate it the other way. Cool. Now, if you're not familiar with this, I highly recommend taking a look at the unit circle. You've probably seen this a long time ago, but we have radian values that can convert to degrees and vice versa. Okay, let's comment this all out for now. We will revisit this in a bit, and let's just copy and paste our old one again. So I'm just going to copy and paste this, and I just want to cover a few last concepts before we close out this video. And this time I'm just going to do positionLocal, just like positionLocal. Now, of course, you're not going to see in Blender what you see in Three.js if we just use positionLocal. And that's because we need to convert the axes, because in Blender, up and down is Z, and here it's Y. So we can do that right over here. We can const corrected position. And then I don't remember if I talked about it earlier, but this is pretty much what we're called as swizzling. You just switch the order. So I'm going to start positionLocal.x is the same in Three.js and Blender, but we want the Y axes to be the Z axes from Blender. And then for positionLocal.y, we want to negate it or make it negative. So if I go to Blender and start a new general file, and I'm just going to say this, you can see that we start from this sort of angle. So technically what you do is you actually start from here. So Y going away from the screen is in the positive direction. Whereas in Three.js, the Y-axis, or in the Three.js it will be the Z-axis, the Z positive direction is toward yourself or outside of your screen. So these are opposite, and that's why we negate them. So in Three.js, I changed the Z-axis in Three.js to Y, and then I also made it flipped because it's going the other way here. So that's all that is, and we can just use corrected positioning here instead of positionLocal. Hello, I am from the future. Now, this is typically how you convert from Three.js and Blender to each other's coordinates, but you can see this is actually not exactly what we see in Blender. This is down here, so we need to also negate it on the Z-axis. So I can just do negate over here. And now you can see we get what we see in Blender. This error isn't going to change anything about the future things that we do in this video, but it's just something that I wanted to point out. If you don't want to use the Blender coordinate system and just want to use positionLocal and a plane that you create in Three.js and just attach it to that shader material, you can totally do that. That's what we did earlier. But since I want to work with Blender, I'm just going to swizzle it, but you can treat it effectively as the same thing. Now, I don't want to force you down to a specific approach. And typically, I mean, it's also totally fine just to leave this as final color and remove this rather than rename it. However, you will often find that when there are like static transformations that never change, that affect everything after that, you'll find a lot of people give a semantic meaning to their name. That way it's easy to understand what it's doing at that point, rather than just tacking on everything to the final variable that you return. So in this case, it's probably more common to use a separate variable name than just gem final color as this one, but you could totally do that as well. Okay, so maybe now we can do some really common things like drawing a circle. I'm going to be honest, when I first started working with shaders, I had absolutely no clue how to draw a circle. So you might be thinking right now that you have no idea. So that's totally fine. At this point, I recommend you Control A, Control C to copy the entire Three.js shading language, have this prompt how to draw a circle in Three.js TSL shading language, and just hit enter into AI and see what it gives you. Now, you might be looking at this and you're like, what the F am I looking at right now? I don't understand anything right here. Please help me. Please help me, Lord. I don't know what I'm looking at right here. But that's totally okay because here they're using UV. You know, we want to do positionLocal. So, like, can you use positionLocal instead, bro? Instead, brother? Cool. Now this is what I'm talking about right now. So try and identify the things that you know and then the things that you don't know. So here, positionLocal.xy, you might not know what that does. You can ask AI to explain it. But basically it's creating a vec2 and of the x and y coordinates and just putting it in position. Then it's taking length. So what exactly is length? Again, you could just ask the AI to explain that for you, or just look it up in the Three.js Shading Language wiki. So since we found something new, let's just stop over here. Let's not even worry about this for now. So I'm going to come over here and I'm going to do corrected position dot assign corrected position, and I want to take the length of the corrected position. And let's just make sure this is imported from TSL and take a look at what we get. We get something that kind of looks like a circle. Now notice how they're going with the variable root, which you can totally do as well. But here I'm using the assign here, which is basically just saying set this equal to this new thing over here. If you're just using positionLocal and you're mutating this, that's when you use toVar. But since we're creating it as part of a vec3, it's already going to be mutable. If you don't know what I'm talking about, that's totally fine. It's really nothing important to know, other than just choose whatever approach works for you. You don't have to be a coder to work with TSL. Okay, so of course we want to see if there's a similar thing. Can I search up length? And it looks like there's one from vector math. I think that's the one we want to do, so I'm just going to drop that in there. And wow, that looks exactly the same as I do over here. Now, the reason you're seeing the background color change is because I actually added an orb rather than just the actual background itself. So it's being updated with that material as well. If that bothers you, you can check for the background sphere name over here and give it a different material. So it's not using that, but I'm just going to live with it for now because we'll get rid of it soon. Okay, so at this point, if you have no idea how they got these values, this is when you should stop, and before even continuing on over here, just try and figure out and make sense of what you're actually doing. Of course, you can ask the AI again if you need more clarification, but we have enough knowledge to understand what we're seeing. So we're using the object coordinates, which means if we pick a point, let's assume this is the plane over here. Sorry, that's messy. It's 2 by 2, which means the farthest corner is 1 over here, and this is -1. Those are our coordinates. And remember, we said all points are technically vectors. So when we pass in all our object coordinates, you can imagine we're passing in a lot of vectors, and it's just taking the length of each one of those vectors and displaying it as a form of color. So that means if we pick a point, it's actually a vector that we're taking the length of. So let's just, for simplicity's sake, pick this, and it starts from the center, 0, 0 over here. Well, now we just take the length of this vector, but how do we do that mathematically? Well, if you remember, it's just the distance formula. So it's just 1 minus 0 squared, 1 minus 0 squared. So in the end, it's just going to be the square root of 2. So the square root of 2 then is 1.414 blah blah blah. And then the distance between 0, 0, 0 is just 0. So that's why we see black here. This over here goes to -1, but if you put it into the distance formula, you're going to get the same result, that this is a distance of like 1 point. I forgot what it was, like 1.41, yeah. That's actually exactly why we actually see full solid white way earlier, and then we just keep seeing white, because it's just clamping to 1 after a certain threshold. So the distance vector of 1 is probably somewhere around here. Okay, so now you understand this, we can move on to the next thing the AI showed us. A radius and a smooth step. Again, I don't know what that's doing, but I'm just gonna copy and paste it and work through it. So let's just come over here just to see what it does. Let's shift alt down arrow just to copy that, and we can just leave const radius up over here. You can put it outside the function too if you want to, not really a big deal. And I just want to see what we do here. So we would just copy and paste this and copy over here. And instead of distance, so this should be fine. Let me see. Let's get rid of that. Instead of distance, we'll just do corrected position because it's already being assigned to corrected position. Here they are doing the variable root, but we're using assign. So you can just see it's like tagging onto itself over and over again. So I'm just going to save that. And it's like, OMG, we got a circle, guys. Oh my God. Oh my God. But like, why is it, what is that fuzzy stuff? Like, what is that? Dude, can you make it sharper, please? And wow, the AI is so smart. It's telling me to make this smaller or use a really sharp edge called step. Maybe that's what I'm looking for. So I can look for step over here. And you can see generate a step function by comparing two values. So it takes an edge and a vector 1, I assume. So because we're taking the length, everything is technically a vector 1. So maybe we can just do step. And the first parameter, I don't know, maybe we can just like try 0.5 and see what that gives us. And let's make sure to import that as well. And wow, that is so interesting. So let's take a look at what step is doing in a little bit more detail. So remember, we originally had the length, which was like a smooth gradient. Now what we're doing is comparing that length to this edge value that we put in here. So wherever 0.5 is in terms of the length or distance away, so we can assume all these vectors are 0.5 distance away, just clamp it to 0, otherwise set it to 1. So how do we do that in Blender? I hope there is a step. So let me search for step. Well, that's not, unfortunately, to my knowledge, there is no step translation directly to Blender, but it's fine because Blender is still vector software, so there should be something here. Maybe we can ask AI, but it also says comparing two values. So maybe we could somehow compare two values. So one way is maybe we can search for compare. And indeed, we do have this converting math node here called compare. So if I just slap that in there, what do we actually get? That's so interesting. Now, this is not a one-to-one translation. You can see if I adjust this, it's going like that. You can also see the color is inverted compared to our step function. You could also do something like here, adjust the scale, right? And that would adjust the coordinates, but it would have the same essential effect as adjusting this value here or our step value. You can prove that in Three.js code, again, if you want to translate that. Right, there's other ways to scale that as well. You could come over here and search for multiplied vector math and plug it in here. Then you can set it, let's say, like at 2. And you can see it has essentially the same effect as scale. You can also use other operations like floor. And of course, there's probably other nodes that you can intuitively think that you could use, right? Like greater than or less than. This would make some sense, right? You could also probably work with ceiling. So you wouldn't have to use this node. You could just trial and error with these nodes. I'm not going to cover every single way to make an adjustable circle in Blender because there's so many ways and orders to do it, just like how there's so many different ways to end up with the same number in a mathematical formula. The entire point here is just to have fun experimenting, and when you have to, sit down and do the math and try and figure out why you're seeing what you're seeing. So, I mean, I actually don't even know if this would work or not. I think the default value is going to be 0.5 for the vector math one as well. So we can just search for that and just plug it in over here. And I'm just going to mute this one. Looks like it's inverted. You can invert that if you want to, but you know, close enough. So we could probably adjust this here or here. Anyway, what we did create is we created a mask, right? It's a black and white image, and we use this for masks all the time in Blender, Photoshop, Substance Painter, you name it, is probably there. So why don't we use a mix color node? So we'll just do mix color node and use that as our color, our factor, and let's just choose two random colors and plug that in. That should get us exactly, it does. It changes the color. Now, we could ask AI to do this for us, but how about we just try and figure it out ourselves? So we used a mix node, and we know we need two colors, and we represent colors with vec3s for an R, G, and B channel. If you want, you can do alpha as well, but I'm just going to stick with full visibility. And sorry, I just realized this is in a wrong order. Technically, this should come after. It doesn't really matter because it was just a reference to that, so order didn't matter. And if you wanted to do final color like here and then switch all these with final color, you can do Control D to select the next instance. You could do that as well. Honestly, it doesn't really matter. I think I'm going to still stick with corrected position and just reassign it to final color after. So we know we need two vectors for two colors. So why don't we just create color 1 and let's just make it full red and shift alt down arrow and let's just make this one full blue and change that to color 2. Now, is there a mix node? So let's just search. Is there a mix node? And indeed there is. And then there's a factor here, which is great because that's exactly what we want to go for. Now remember, this entire thing is our mask. So we can't just like slap corrected position in the mix function. Like originally all this logic over here was our color as well, but now we're like disconnecting it and putting it as part of a mix node. And then we have our two colors. So we have to do the same exact thing here. Final color is no longer going to be the corrected position. On its final color, we are going to start off as a vector 0, 0, 0, just like the mix node itself. So we'll come here and let's just do 0, for all three channels. And now we can just come over here, final color, dot assign, and we want to mix color 1 with color 2, and we want to use our corrected position mask. And take a look at that. We have indeed the black area is red and the white area is blue. Now again, you can just ask AI, dude, I have a white and black circle, help me, and it'll give you a solution. I actually like their solution better here. This is one of those times where splitting it up into variables looks a lot cleaner. Here you can see this kind of looks a little bit hard to understand, where theirs seems to be pretty intuitive. It's like create your two colors, create your mask, and then the final color is just a mix between your two colors and your mask. So this is intuitively easier to understand than what we were doing with assign. So for this, I would probably go with the AI approach here. So I think we built a strong enough foundation where I can just speed up the process and kind of just talk about some cool stuff to do and tips and tricks for the rest of the video. If you don't want to watch, that's totally okay. It's just now your time to completely try and experiment stuff on your own and Google what the functions do, ask AI, and try and fail over and over again until you start to actually understand it. So one thing that is really fun to do is play with the time variable. And this is a really nice way to be able to tweak values without having to set up an interface. So let's say instead of the red channel, I wanted to change on time. And you can 0 to 1, and then it's just maxing out at 1 because time is increasingly going up. So if you want to do that, well, you can do something like sine of time. So let's just pretend x here is time, and it will always be increasing. And you know that with the sine graph, it's always going to go between 1 and -1. So that's why you can see that right now it's going to black and it's going to red. Of course, you remember that you also have shifting, so you can just do like +2, it'll shift up, and now it'll go to between 3 and 1, which means if I do .add here and I do 3, it's just going to stay permanently red because it's oscillating between 3 and 1. But then you also have things like the amplitude, right? So now it's going 5 and -5. And then you also have the frequency, so you can just do like 10 here and it goes really quickly. So you could just come over here and do time and just multiply it by like, let's just do 10. And you can see now you have something blinking. Just like that, you got something pretty cool. You can do this for other things. I mean, let's just leave this as 1. Or maybe we can put the time over here, right? We can try time over here. And what is that doing? Well, it's expanding, right? Because the step is increasing over and over and over again. Okay, so I'm just gonna push this. If you want to grab it, you can. But it's nothing really that special. So just look for that commit if you want to find it. Anyway, let's revisit this because that's exactly how I color this entire scene. So I want to, let's see, let's just get rid of all this and let's recomment this. And now what I want to do is be able for each one of my objects, oh, sorry, this is dead code over here. For each one of my objects, I want to give some sort of variable. Now you can just use traditional variables and that would be fine in a lot of cases. But for variables that you're tweaking, like with the UI, you can see dynamic values right here. We want to use this thing called a uniform. There's a reason they call it uniform because the same uniform executes for every pixel on your fragment. There's also this thing called a varying, which you transfer from your vertex shader to a fragment shader that gets interpolated. Basically, you give data to each vertex, and then it's interpolated along the fragment shader. A little bit more complicated, we'll cover this in future videos. For now, we're just going to stick with uniform. So when it comes to user interfaces, lil-gui is a very common one. You can see some of the cool stuff they can have, like toggles, drop-downs. Really easy to set up. You just pass in your variable, a title, a range, or whatever kind of option that it is. For us, it's going to be mostly sliders. Leva. This is really common for React 3.5. lil-gui is very common with vanilla Three.js. So we have rotation, we have translation, so now we should have some scale. So let's just do scale here. Again, you can do scale before this as well. It would be the same, but I'm just going to put it here. It doesn't really matter. So of course you can just ask AI to do it. You don't want to waste your time doing it. So I just copy and pasted my function, but I also copy and pasted my entire code. But I specifically said, just show me what I need to change and add things. That way I don't have to wait as long and I could explain it. Sometimes I do just copy the paste and hold the whole thing. For smaller projects like this, that would be fine. But in this case, I just said, just show me what I need to change so it's easier to understand. But yeah, you can see that prompt if you want to. And now here you can see that it gave me what I wanted. And I'm just going to place it over here. And it's fine to leave the GUI stuff here. If you want to categorize it up there, that's totally fine as well. And let me just copy this as here. Let's make sure uniform is imported. Now, if you look, Claude messed it up. Usually it doesn't, but this time they messed it up. And when I adjust my sliders, it's not updating anything. And that's because you're missing the onChange function that comes by default in lil-gui. So I'm just going to copy that and put it over here now. So now when I adjust this, this should be good to adjust. Super cool. And then I have this offset over here. And then I have the scale pretty much. So pretty cool. I kind of have like full flexibility over here. I also don't want to just use black and white. So I'm also going to add those uniforms as well. And I'm going to set default angle to 0 or 0 over here. And I'll leave the scale at 1. Let's add some lil-gui over here just to update that shape. And let's add those uniforms over here. And now since this is black and white, we can just use that as our mix value node. So I just got it from the AI. You already know me. But here you can just see that rotate X, this is going to be our mask. So I'm just going to get rid of that. And now you can see that's what we have here. So I can adjust this color. I can adjust this color. Super cool. If you want to validate it, you can change this one to black and this one to white, and you can see that it works. So I just want to reiterate, this is not the same thing that we see here in Blender. There is a color ramp here instead, and we're doing the dot product. You can do the dot product if you want of a directional vector of 1, 0, 0. It's not needed for a very similar effect to what we have. I'm planning to cover color ramp in a later video and how to make one with TSL. So it's not going to be in this video, but if you want a hint, you can use smooth step. And if you want to make it constant, like this, you would use step. Hopefully that kind of gives you some intuition there on how you would make a color ramp. You could also do it with things like select. Again, if you don't know what these do, it's like totally okay. But just for hints, if you wanted to do an actual color ramp rather than what we're doing. Now, it would be extremely tedious and it would be bloat up the controls if we created a separate control for every single object in the scene. That would just be impractical. So what I recommend doing is in Blender, give it some sort of naming convention. If you want to bulk rename, you can do Control F2 and like search for something and like replace it. And create a map in Three.js. So like if I come over here and it's just like if child name, let's just assume we are looping through the child and we're checking for the child name. And then we can see is like, does child name contain blue underscore stripes? If it does, give it a custom material with so-and-so uniforms, which we need to add in there a little bit later. So give it a certain rotation, right? You'd have like, I don't know, you would have the name. So I forgot what it was called. Let's just assume it's called blue. And you check for blue, value a rotation amount, right? Like 0.4 or something, blah, blah, blah. And then an offset value of like 0.1 or something like that. So we can just do like const material params uniforms. I don't know, it doesn't really matter. Now, this would be a great approach. You can use a combination of approaches, but this would be a great approach if you only have like a few objects that you need to adjust, and they kind of like all use the same sort of material. If you have many materials with many configurations, your map would be very large in Three.js, which is fine if you want it that way. But an alternative to that then is just to put a naming convention for each of your materials. So let's say I have this one over here. Its location is 0.18. So I could do cloak, but I could also do offset, and it's really up to you what naming convention you want to do. I might just do 0.18 here and do another one, and its rotation is 90 degrees. So I'm already only rotating along the y-axis in Three.js, so I don't have to specify it, but if I want to, I can do rotate y. But if you want to, you can do rotate y and then maybe type 90 there. And if you want, you can do like scale 1. I mean, why not? Or whatever. If you want to do other stuff like do underscore between every single one, you can do that. You can split it there as well. So there's lots of ways to name convention your thing. For colors, you can put the hex value here if you want, like H3, right? Like you can just place the hex value as part of the string as well. So this would be color 1. And then this would be like color 2 or something like that. And your code would automatically detect that. Now you would have very long names for sure. So I feel like for some things you can use like this is fine. And then maybe for the colors in Three.js, you create a map for the colors rather than having to type the hex code here. You could also actually just part of the material name itself. And you could check for child.material name rather than the child name itself. Again, I had like 4 materials that I wanted to customize. I had like 9, but I got lazy and just typed 4 just for demo purposes. But of course I used AI to generate the map for me. I just told them what uniforms to set which values based on the material name. So here it gave me a function and it basically created me a map. Well, this is a chain of if statements, but you could make a map as well. And here you can see I'm loading a new model scene2 over here, and it's just checking for the name over here. And then for this one is checking the material name, so child.material.name. And then if it's one of these, it's going to go to that function up there and just set the appropriate uniforms based on the name. And yes, you do have to create a new set of uniforms if these values are different for every single material. So that's what that is. Again, if you're not tweaking it with like time or like dynamic updates, you could just do basic parameters, but oh well, not really a big deal. So I just made a push if you want to download the new starter files for these following sections. Okay, so I'm starting from this again. Again, it's just a typical position local, just with Blender coordinates instead. And the first tip I want to give you is sometimes you will make changes to other coordinates that lead to unexpected changes behind the scenes, and you'll get confused when doing mathematical calculations. So when you get something that doesn't seem to add up to your math, you might be actually affecting another coordinate that you don't intend to affect. So here, if I just take the length of corrected position, we've seen this before. Now, take a look at what I do with fract. Again, you might not know what fract does, and that's totally okay. When you don't understand what something is, really just type it out in ChatGPT or something, some AI, and have it do the mathematical calculation for you. Intuitively, what it did was shift the origin to this corner. So in order to recenter it to see what we had initially, you can do this over here, which is another tip and trick I have. Instead of doing assign corrected position dot sub 0.5, you can just do sub assign. There's also mul assign, probably div assign, and add assign as well. There might be others, but those are the ones that I'm familiar with. And now you can see, well, you pretty much see the same thing. Let me just take it off. You won't see it on my code, but I'm just going to comment that off. You can see that's what we had originally, and that's what we have now. It's just that thing being repeated 4 times. And now let's take a look when I take the length of this. Why is it now we are not seeing completely black in the center? Why is it like gray and expanding outwards? We get the intended behavior, but we don't get the same color. Like, you would think that just because we made 4 clones of the original thing, it should look like this, right? All we did was make 4 clones. But here's the thing. This subassign, what it's actually doing is subtracting all coordinates. So there is a z coordinate here that it's subtracting from. And that's what's causing this center here to be not completely black, because there's a z coordinate in here that's affecting the end resulting color. The good news is, just because it's not the intended results that you expect, doesn't mean it'll affect future calculations in what you do later. Because oftentimes you do things like remapping. So even if the z coordinate is off, it gets remapped to a range you work with later anyway. So it doesn't actually matter that the z coordinate is being affected here. Obviously that is a case by case basis, but I just wanted to emphasize, when you're doing math tracing, you might be affecting unintended coordinates. And don't forget to take that into consideration when you're doing things. But there's a lot of times where affecting those other things doesn't really affect how you proceed with the final procedural outcome. So the second tip and trick I have is to take a look at the Three.js org examples. There's a lot of really amazing things here, and this is kind of like how I learned a lot of what I did. So one of them is the WebGPU TSL editor. Instead of creating your own working environment, you can just write some simple TSL here, and it'll output in this little demo over here. And it'll also output directly into the lower level code WebGSL. And since TSL also goes to GLSL, you can also see the GLSL version of that as well. There's also the TSL transpiler. So if you're one of the few people that know GLSL, or you're trying to find a GLSL function and convert that into TSL code, you can actually put it in here and it'll output into TSL for you. So if you're not familiar with the space, this is a very common list of GLSL noise algorithms. There's like Perlin and Simplex and all these other ones here. And these are all currently in GLSL. So if you want to use them in TSL, well, you can just slap it in here and it'll give you the TSL version that you can copy into your own code. There's also really awesome demonstrations of combining stuff. So here, we didn't fully cover it, but you kind of intuitively get the concept of how to make a flame like this, right? So if you click the code button, you can see that it's like always think about in layers or in nodes. We didn't cover a lot of this, but intuitively you kind of just already understand how to layer things and make something like that. And that's like the really cool stuff about it. Like take it one step at a time, just the same way we did with AI. Just use one, see what that does, try and calculate the math, do another one, so on and so forth until you get through. There's also really cool ones like this, creating VFX. And then there's also other people that have converted Blender tutorials into TSL nodes. So this one is going to be very, very helpful. It's a procedural wood material created with TSL. And you can see that this procedural wood material is based on a Blender tutorial. So right over here, and here you can see that he's doing a procedural wood material and he's using a bunch of the nodes and some things that we saw before as well. So this is another avenue that you can take. He goes a little bit fast for beginners, but if you stop node by node, you'll eventually get it as well. Some cool stuff to check out. TSLFX is pretty cool. There's also TSL Textures, which you can dive into the source code and deconstruct if you want to as well. It's also completely open source. Shout out to the creators here of these repos. Another great resource to check out is Wawa Sensei's YouTube channel. He's been touching a lot of TSL recently and even some advanced Blender concepts that I haven't covered on my channel yet, and maybe sometime in the future, but definitely check him out for like smaller bit content rather than long form content like mine. Another great resource for TSL is SBCODE.net. It does go a little bit fast for beginners, but there are a lot of tips and tricks you can find in here, like this over here. In your console, it'll show you your compiled fragment shader. And if your web browser does not use WebGPU, it'll show you the GLSL outputted code instead of the WebGPU code, which is really, really cool. So another really cool thing that you can use are MaterialX noises. Now, I discovered this recently actually myself because it's not officially labeled in the wiki. I'm sure it might be eventually, but it's another really cool thing that you can import from Three.js TSL. You can see there's some noises that you can use by default. Another cool thing you can do is for instant gratification, what you can do is just use what other people have already done, like on WebGPU post-processing ambient occlusion. This is like a really cool thing just to directly just copy it and add it to your code. And there's other ways to implement ambient occlusion, like baking it in Blender, but if you just want to see something cool and make your models pop, you can just like copy and paste the code. And one of the really awesome things is once you start using some of the other things that other people create, you start connecting dots to other post-processing tricks that other people use. Like by default, there's something about this model that just makes it feel so much better. And it's actually the subtle ambient occlusion you can see around here. So if I come over to settings, model inspector, and turn off no post-processing, you can see that with the final render, with the ambient occlusion, it definitely looks a lot different. Another tip and trick I want to say is try and avoid if statements as a general habit. These are very computationally expensive for GPU, so try and avoid if statements if possible. There are some cases where you have to use an if statement or it's actually better, but generally it is a traditional habit to avoid if statements if possible. So here you can see I'm using an if statement to draw a white line over there, but you can easily just use a step function instead. So this is what this example is over here. It's using a step instead of an if statement, and you can see that it also does the same exact thing. And then even more, if the value is the same, like bottom down here and bottom up there, and it's like a centered line, you can just use like absolute value rather than using two separate values to check from. So there's a lot of subtle, small tips and tricks you'll pick along the way as you continue your TSL journey. These are just some of the ones that I want to share for the time being. I'll definitely be covering a lot more in the future. Shout out to my 3 Patreons for feeding me before I become homeless. Yeah. Thanks so much for watching. Take care, and I hope to see ya in my next video. Peace out.